So we left off introducing this concept of boundary work. We said that volume does not change spontaneously. So if we compute W sub B boundary work, if I integrate, again, work is caused by a force. Now I'm going to draw an F here, and I'm going to say, well, it's not actually an F. It's what causes the force is pressure. So the integral of pressure, and instead of traveling across a distance, that pressure propagates through a volume, specifically a volume change. So the pressure causes the force, and the distance traveled is throughout the volume. Okay, and we derived in class how we got there through a constant area multiplied by a change in distance. Area times distance gives me volume. Okay. Why the out term? Well, this is just kind of a traditional sign convention we would use in a thermodynamics course. Again, the goal is we want to put heat into a system. That system is going to expand, and as that system expands, we're basically extracting work out of that system while it expands. So this is the quantity we want, is we want work out. When your engine is burning a fuel source, gasoline, octane, something like that, or compressed natural gas, when it burns that generates heat, and that heat causes a pressure, and that pressure causes a change in volume within your engine, and that volume change drives your drive shaft, and that's the work that you get out. So as that system expands, it pushes the surroundings out of its way. It puts work into the surroundings. That's work going out of the system. So what we have here, and by the way, if mass is constant, you can pull that out of the integral, and this is something we will commonly do, right? If m is constant. This is also true. Again, I'm basically saying mass times a change in specific volume is equal to a change in total volume. The mass is constant, so it comes out of the integral. Okay. Now, again, we were talking about why is this an out term? If it's expanding, so expansion, that is where you are going to a larger final volume. Notice the sign of the integral if this is the larger term. So it's this minus that. No matter what the function is, it's this minus that. So if this is the bigger term, then your boundary work in the out direction is positive. Okay? If you have compression, that's where it's going to a smaller volume. Sorry. The initial volume is the larger quantity. It's going to a smaller volume. Well, it doesn't do that spontaneously. Remember, I said I've got a system here, and if I want to compress it, I've got to put work into it. Right? It's the opposite of work out. So if I compute work and assume that it's in the out direction, I'm going to get a negative quantity. So it's actually the opposite of work out. This is telling me it's actually work in because it's being compressed. So if the system expands into its surroundings, it's putting work into the surroundings. That's work out of the system. If the system is being compressed, that means the surroundings are pushing its way into where the system was. The surroundings has to push the system out of its way, so the surroundings are putting the work into the system. If you want to compute the work in, this just switch the sign of the integral, put v1 up here and v2 down there, and compute, and you'll be computing the work in. It's a gag reflex for me. I will always compute the work out. If I get a negative sign, that just tells me, oh, it's actually work in. You can plug it in the first law equation as a negative work out, or you could plug it in as a positive work in term in that case. However the sign works out for you is fine with me. All right. So that brings us then to first law for closed and stationary systems. So please tell me you know at this point what a closed system is. If not, you really have some work to do. That's putting it nicely. You really need to know what a closed system is at this point. So what is a closed stationary system? Well, again, if it's a closed, first law for anything, right? First law for anything says take all the energy in, subtract all the energy out. That equals the change. Okay? In minus out equals change. And that change, I should say, is delta E system. Okay? So it's in minus out equals change. In this case, delta E system. So the energy into the system minus the energy out of the system is equal to the change in the energy of the system. For a closed system, the way energy can come into the system could be heat and work. So I'm going to add the heat in, I'm going to add the work in, and I'm going to subtract those quantities going out. I'm going to subtract the work out, I'm going to subtract the heat out. I said those backwards. And that's going to equal the change in the energy of the system. Now, if it's a closed system, again, we should know that means mass is not crossing the boundary. Therefore, the mass is constant, so I'm going to factor it out. And the types of energy that can change for a system, this one you want to pause if you don't know this one. What are the types of energy that can change for a system? Pause and go find that out. Okay, you got it? Should be internal, kinetic, potential. Well, if it's stationary, there's no change in potential, there's no change in kinetic. I've only got internal. Right? The change in the energy of the system is the change in all the energies of the system. If it's stationary, the only one that's changing is internal. Okay? So how do I write a first law equation? Well, I could write this out and then just go look at my problem and say which of these make sense, which of these do I know are zero, which of these am I going to assume are zero. If I'm looking for the work out, I don't see anything doing work in, or if I don't see anything doing work at all, I probably just assume both work in and work out are zero. Can't do that if the volume changes, by the way. I've got to compute a boundary work out term. If there's anything else applying a force or electricity, then I'm going to have a work term. Could be in, could be out. I got to look at the system. Heat, well, it depends on, do I know if it's adiabatic or well insulated? That tells me there's no heat transfer. Otherwise, are they asking for the heat transfer? Then yes, I'm going to have to solve for heat transfer. If they need to, in Chapter 2 we could get by saying, well, they didn't tell us anything about the heat, we're just going to assume it's zero. Now, Chapter 4 we don't get to do that. Chapter 4, normally I need to assume that there's at least heat in and or heat out. Probably, and normally we can assume there's one or the other. Okay. Writing a first law equation. I don't know if I've ever written this out formally for you guys. So let's write that here. Writing a first law equation. Step 1. Draw your system. Step 2, draw any energies or mass crossing the boundary. Step 3, add ins and subtract outs for left-hand side of the equation. Right? In minus out. These are the four things that you have to choose from. Right? Could have multiple works. Could only have one heat, maybe. I don't know. That's why you draw your system and you draw the energies crossing the boundary. If it's a closed system, you don't have to worry about mass. It will follow the same procedure if it's a control volume, by the way. The right-hand side is the energy change for the system. Right? By the way, that is M delta U for closed stationary, and that is 0 for what we call steady flow. A lot of texts will call this steady state, for steady flow control volumes. All right, so the right-hand side is going to be either m delta u for a closed stationary system or 0 for a steady flow control volume, depending on which chapter we're working out of. Here we're kind of focusing on chapter 4, so for us it's going to be m delta u. Because again, there's no, if it's closed, the mass is constant, so it factors out. And if it's stationary, two adjectives there. If it's stationary, there's no change in kinetic and no change in potential energy. So this is the procedure for writing a first law. Remember, I drew out kind of a nice set of steps for using property tables. This is a nice set of steps for writing a first law equation. By the way, the timed questions on your exam, the one you'll have 5 minutes to answer very quickly before you have to write a solution for the entire problem, I will ask you to, what is the result of this process? I won't ask it in so many words. I'll say, which of these is the correct simplified version of the first law equation that you would use to solve this problem? You'll need to be able to go through this process very quickly. How do you study for this exam? Go through as many problems as you have time to do and do this procedure for them. And then check it against a solutions manual, an online resource that you trust. I don't know if I'd trust some of the ones you guys are using, but anyway, some kind of solutions manual or some kind of resource, or ask me. Send me an email and say, hey, would you mind looking at these first laws and give me some feedback? Send me a picture, email them to me, submit it to one of the assignment folders, and then email me and say, hey, I uploaded a whole bunch of first law equations. Would you mind looking at those? That's okay. I'm happy to do that. Okay, pick out some problems, practice. Get to where you can do this fast. Just like using the property tables, get to where you can do that fast. You don't want to have to try to figure out how to do this on the exam. You will not do well. You need to figure out how to do this before the exam. Okay, so just practice this. How do you study for this exam? Practice this process over and over again on all the chapter 4 and 5 problems you can get your hands on, and then find some more on the internet and do some more. Okay, and then get some feedback. Then check those. See, did you get your first law equation right? If you can do that, then the rest of it is algebra and units. Now, you need to be practiced and good at doing those. But if you can't do this, well, this is the bulk of the point. This is really what we're trying to test you on. Okay. All right. That's first law for closed stationary systems. A little insight into first law for control volumes. Now, before we talk about control volumes, we do need to talk just quickly about conservation of mass, because what is a control volume? Well, that's a system where mass crosses the boundary. Right? So the conservation of mass, just like any other conservation law, says that n minus out equals change. If I add up the rate of mass coming into the system, subtract the total rate at which mass goes out of the system, that equals the change in the mass of my system with respect to time. Okay? How do I find the mass flow rate? Pause and go look this up if you don't know this, but you really should know this expression. There's multiple versions. You should have a pretty good idea what this looks like. You should be yelling at your screen right now telling me what these are. What are these? This is rho times the volumetric flow rate, right? Mass per volume times volume per time gives me mass per time. I can find that volumetric flow rate using the cross-sectional area multiplied by the speed at which the fluid flows. Density, area, speed gives me m dot. And remember, the reciprocal of density is the specific volume, little v. Some of you guys are mixing these up on your homeworks, and I've tried really hard to make this clear. These are not the same thing. There are 3 different v's here. You need some way of knowing which one is which. Your units will help you with that. If some of you guys if you'll quit ignoring your units, you'll do a lot better. You don't have to write them down, but you do have to keep track of them. All right, we'll come back on the next video.